optimization of sliding mode control strategies has significantly contributed to the control engineering community. With more than 40 research publications in reputed journals and conferences and a book chapter on optimization of terminal sliding mode control, Dr. Laware had established himself as a leading expert in this domain. He also serves as a reviewer of several reputed international journals, including Elsewhere ISA Transactions, Journal of Process Control, SN Applied Sciences, etc., which reflects his strong standing in global research community. Today, Dr. Laware will be delivering a talk on optimization of sliding mode controller parameters, a topic that is extremely relevant for advanced control applications in modern engineering system. So we are truly honored to have him with us. I warmly invite Dr. Ajit R. Laware to begin this session and share his valuable insights with us. Over to you, sir.
Thank you, Marin John, ma'am. Am I audible to you, sir?
Yes, sir.
Okay, sir.
Yes, yes. You're audible.
Can I share my screen now?
Yes, you can share.
Sorry. काय होत आहे?
Yes, it is
Sir?
visible. Yeah, it is visible. You can make it full screen.
Is it visible, sir?
It is visible,
Yeah, yeah.
but you can make it full screen. Full screen.
एक मिनिट हा. Full screen.
There is an option at the bottom.
Hmm.
Zoom in and zoom out above that. Zoom in आणि झूमच्या बाजूला इकडे. हा,
एक मिनिट.
त्याच्यावरचं, त्याच्यावरचं, त्याच्यावरचं. हा.
Zoom in.
हा, here you can see
एक मिनिट इथे.
full screen mode at the bottom. Full screen mode.
Yes.
Ha. Yes, perfect. Yeah.
कुठं? Hmm. Sir, am I audible?
Sir, you are audible,
Yeah.
but your screen is not there now. This is okay.
Yes.
Perfect.
Yeah. So, very first and foremost, good afternoon to respected coordinators, Professor Dr. Ravindra Munje sir and Professor Marin John ma'am, and my dear participants. It's a great pleasure and honor here to be here as a part of 4th International Faculty Development Program on the advanced topics in control system. I sincerely thank the organizing institute for giving me this opportunity to share my work with you. The talk roadmap is classical SMC. Just here, I will be with the quick recap with the example on the heat exchanger, the classical sliding mode control limitations, SMC tuning, that is Nelder-Mead search optimization algorithm, then one level control example with the non-dominated sorting genetic algorithms second, and multi-objective particle sum optimization. And last application, it is based on the same level control plant, and the optimization algorithms, implemented optimization algorithms are Jaya and artificial bee colony optimization. Then I will be the with comparative insights and practical observations, and open research area I will be discussing as per the Graduate School on Advanced SMC organized by IIT Jodhpur, dated on 5 to 10 December 24. Then selected publication list, my selected publication list I will share with you, and finally the references. The real-time plants, these are always with the parametric uncertainty and external bounded disturbance over there. Despite of uncertainty and disturbances, controller must regulate the plant, and the output it should track towards the set point value. But the plant output, it is basically the function of, or it depends on the sensor noise, load changes, some unmodeled dynamics. And due to this, the PID often fails to provide the satisfactory performance. And you are well aware that this PID for time delay system, it never gives you the satisfactory performance. Then it has to routine again and again. Then that derivative action, or there may be the kick of derivative action if you use the PID controller. So uncertainties, nonlinearities, and disturbance, they are posing the challenging problems in the control area. Again, there are some controller tuning issues are there, and this fine tuning of controller parameters, it needs the fine tuning of controller parameter over there. No doubt here there is a need of a robust control method over there, and hence the sliding mode control SMC is one of the most robust control method, but its disadvantage is the chattering that that we will see in the subsequent slide over there. Now, one would go for the higher order SMC or some super twisting algorithms over there. But super twisting algorithms and higher order SMCs, they need more information over there. And hence, some of the researchers like Oscar Camacho and Garcia, they told, or they written, or they published with their paper, the first order plus date time model, they are very efficient for representing any process control system. And here's the need of sliding mode control over there. From the initial condition, the system states they are approaching towards the sliding mode condition, and S of t is the sliding surface, and if S of t into S dot of t is less than equal to 0, this sliding condition fulfills, then your system trajectory, it goes towards the user defined sliding surface. But once it reaches to the sliding surface in the zigzag manner, it reaches to the origin, means it is a asymptotic stability over there. So this signal, it is non-deterministic and high frequency signal which excites the unmodeled dynamics. There is a wear and tear of actuators, and there may be the actuator saturations and all that. So this chattering and parameter tuning complexity pose the SMC disadvantages. As an example, this is the state space model over there, and A1, A2, and B, these are the bounded parameters, where A is bounded in between 5 and 10, whereas A2 is bounded between 1 and 4, while B is bounded between 1 and 2. And here linear sliding surface, it has been used, eta equal to 4x1 plus x2, and control law, it is shown over there. So here in the control law expression, rho SGN of rho Hn of eta is the discontinuous control, and the part before that 1 by b a1 x1 plus a2 minus 4x2, it is equivalent control over there. And main condition rho, where rho is the discontinuous gain, it should be the positive real number. If you observe over there, the states, system states or system trajectory x1 and x2, they are approaching towards the zero, means stability of it shows the stability of a closed loop control system. And while coming to the second diagram, that is u, means controller output, initial very sharp peak or very sharp switching takes place over there, which is up to the 20 unit. And this sharp switching, it indicates the faster convergence over there. And if you observe the controller efforts or control input, it has a much chattering from plus 10 to minus 10, means plus minus 10. So this classical SMC always gives you the chattering, and this is the nature of our trend of sliding surface over there. And this is the phase plot of x1 versus x2. Then this is the chattering in the SMC. Now this is about the conventional discontinuous control, like K Sgn of S of t, means switching gain and Sgn of sliding surface function, it is there. Then that is the classical SMC. And this U, it is with the boundary layer techniques, where this eta is called as a boundary layer thickness, and that is nothing but the 0.1. So with the boundary layer technique, this is the response, closed loop response, and the nature of the control signal or control input over there. So this chattering, it has been reduced in the boundary layer technique. And also x1 and this states x1 x2, they are approaching to the zero, means there is a closed loop stability, it is there over. Then this is the convergence of sliding surface, and these are the state trajectory, which increases the smoothness of the convergence. As far as the practical problem of a control system it is concerned, the model plant mismatch, then unknown disturbances, parameter variations, and unmodeled dynamics are the major control system problems, and hence there is a need of development of robust control method like a sliding mode or some hybrid control strategies. The serious drawback of sliding mode control, they are the chattering, and the chattering is the main barrier. Whereas your controller output U of t may unaccepted by the actuator, and there is wear and tear of actuator may be there, or some fatigue failure it may be there. And non-trivial and time-consuming parameter tuning is the main serious drawback of SMC. To this presentation, I will be highlighting very basic system as a heat exchanger. Then I will explain predictive structure of sliding mode control for the cascade control system, and then evolutionary optimization for the level control system, then optimization with modified objective function, and finally the second order SMC, that is SOSMC, and its parameter tuning. So first, it is very simple and basic system, heat exchanger. So aim is to design the robust SMC and to identify the signal type for modeling this one. This is the process and instrumentation diagram for the heat exchanger system. So two working fluids are there. One is water and another one is a steam. That process fluid water, it passes towards the heat exchanger via the displacement type of pump, and NRV, that is non-return wall, towards the heat exchanger. And another working fluid is a steam. So steam imparts the heat energy to that working fluid, and obviously the output parameter is the temperature. So here T, that is the temperature element. This is the PNID diagram. So actually this setup is available in our mechanical department. Computerized setup is available at our mechanical department. This TE, nothing but the temperature element. TT is the temperature transmitter. TIC is the temperature indicator and controller. TY is the temperature converter over there. And this is the pneumatic valve TCV, and IA is the instrument here. So here, this steam, it imparts the heat energy to the working fluid, and based on the variation of the output water temperature, the signal is sent to the controller. In turn, it gives the signal to this pneumatic control valve, and that pneumatic control valve, it regulates the flow of steam. Hence, there is a regulation of temperature over there. This is simple feedback structure. It is there. Everyone knows that. And this is the feed forward architecture over there. So here, disturbance is the steam pressure and steam fluctuations. You may consider it as a disturbance model. And later on, this first order equation, it is related to the disturbance model. And another one is a FOPDT model. So this is feedback plus feed forward scheme. Simple. Now, the basic concept behind this heat exchanger system or disturbance, it is T equal to GP of S, F of S plus GD of S. So GP of S is nothing but the process transfer function. F is the feed forward controller transfer function, and GD it is there. So F equal to minus GD by GP. So here disturbance transfer function it is there. F equal to minus GD by GP. So this is the perfect disturbance rejection model it is there. And if equation 2, if you place in the equation 1, then T will be the 0. And that's what it is, the perfect disturbance rejection it is there. And in the first lecture, Dr. Raja told IMC, it decomposes as a invertible and non-invertible part. So here GP minus is a invertible part, and GP plus is a non-invertible part. So dead time, it is a non-invertible part over there. So here S equal to C2x plus x dot, and this is the linear sliding surface, or you may use as a S equal to C transpose x over there, where C transpose is this C1 and C2 over there. So here S dot T, equation 5 indicates you the reachability condition as a minus eta mod of sliding surface. Then power rate law, it is there, minus K mod of S raised to alpha Sgn of S. This alpha, it is in between 0 to 1, and it is used for the low chattering purpose. And if you pose the value of K, increase value of K, then that gives you the faster convergence over there. And finally, the control input is control input is represented by equation 8. So, as I discussed earlier, this system identification toolbox of MATLAB, I have been used over there, and best fit for the slow identification, I am getting 82%, while for fast and delta operated signal, I am getting 54 and 62% best fit over there. For ARMA-X model, this best fit, it is in between 70 to 75% over there. I'm getting the process model, heat exchanger model, as a FOPDT. That is, the static gain is 3.8, and your time constant, it is 51 seconds, and dead time is 10 seconds. Then the approximated transfer function, like first order pad approximation, is represented by equation 10. And disturbance model, as discussed earlier, it is the first order model actually. And for this, the PID parameters are shown over there, where N is the filter coefficient. For the IMC, invertible part, it has been used for the controller design purpose. So here, second order pad approximation as a theta by 2, S plus 1, it has been used over there. And QIS of S is the IMC controller over there. And here, in equation 14, 1 or lambda s plus 1, this is the filter, and lambda is the filter coefficient, which has been selected as a greater than equal to 0.8 td tau d. Tau d is the delay time over there, and I have taken lambda as a 4, and already tau d we know. This is the output response of heat exchanger system. So here, if you observe here, classical sliding mode, the rise time, then settling time, all these parameters, they are favorable for the SMC as compared to the IMC. Then feedback and feedback plus feed forward scheme over there. So classical SMC is better than the other control strategies. This is the nature of the sliding surface. And total control input U of t, it shows the chattering here. This is the states of SMC. Then here time domain characteristics such as rise time, settling time, overshoot, delay time, and the standard deviations. These are compared for these 4 strategies. And if you observe the last column values, then SMC outperforms the feedback plus feed forward, and IMC scheme. And here the error indices IAC, IAE, ITAE, and ITAC, these are tabulated here. And SMC also, for this, if you observe, the error indices are also less as compared to the other control strategies. Then this is the robustness analysis, and still, if you observe here, the SMC, it gives you the stable performance, whereas remaining strategy, they are having the performance different than the nominal performance here. And here plus minus 25, sorry, plus minus 25% reduction in gain and time constant of the process, and 25% increase in the dead time, it has been taken place. And here gain time constant, it has been okay. And date time it is never, it doesn't change here, only time constant and date time, it has been changed over there. Then related to the robustness, these are the quantitative performances of heat exchanger system. So here, very classic SMC, it has been simulated to control the outlet temperature or outlet fluid temperature. But this classical SMC, it gives the chattering. This is the biggest disadvantage. But other time domain characteristic or time domain parameters, they are favorable as compared to the other strategies. Next, predictive structure based sliding mode control. Here, time delay controller, it has been designed over there. So later on I will tell you. Then SP, then Smith predictor, then time delay controller. All these strategies, they are implemented for this cascade control system using Nelder-Mead optimization algorithm. So some assumptions are always takes place for the cascade control system. So the time constant of inner loop, it must be great, it must be less than, time constant of the outer loop. This is the relation that must be followed to use the system as a cascade control system. So, and another one is a inner loop must be faster than the outer loop, and its ratio means outer loop time constant to inner loop time constant. It should be theoretically in between 1 to 5, but practically it should be 3 to 5. And to avoid the instability, ratio should be greater than 1. These are the full cascade control system. Here, the inner loop process or secondary process, it must be the fast process, and the outer loop or primary loop, it must be the slow process. So here, level flow, flow pressure, these are the inner loops, and temperature level, these are the outer loop processes. So FOPDT model of the process, general representation of FOPDT process is Km by tau Ps plus 1 e raised to minus tau ds plus 1, where Km is static gain, tau P is the time constant, and tau D is the delay time. So it has been decomposed as a decomposed at Gm minus and Gm plus over there. Gm minus is a invertible part and Gm plus is a non-invertible part. So here cascade control structure using Smith predictor. Smith predictor it is there, and with the help of internal model principle here it has been used. So here in the figure 19, pure output from the model it has been taken and applied to the input side, whereas in internal model principle it is not the case like that. Whereas in the Smith predictor GPD, that is the PD controller, it has been used to remove the steady state error over there. Here the sliding surface it has been chosen as represented by equation 19, where n is the order of the system, it is the tracking error, and alpha is greater than 0. So for first order process n equal to 1, or for second order n equal to 2, like that. So for first order process, your sliding surface becomes u of t plus lambda integration of your error dynamics, that is equation 20. So this total control law is obviously the addition of u switching and U equivalent, that is the equivalent control as well as switching control input. Then equation 20 and 21, it gives you the equation 22, E dot t plus lambda et equal to 0. And for if you apply the step input, as R of t, then its derivative, first order derivative or second order derivative, they are always 0. And we have the expression, this is very important expression represented by equation 23, minus y dot t plus lambda et equal to 0, and the switching control input is a tangential hyperbolic function over there, where Kd is the switching gain, S of t is the sliding surface, and beta is the boundary layer thickness over there. Using Nelder-Mead's search optimization algorithm, lambda it is given by the equation 25, and Kd is greater than equal Kd, that is the switching gain, is represented by equation 26, and boundary layer beta is represented by this equation. Actually, all these equations, they are posed, or they are represented by the represented in the Camacho paper, Oscar Camacho paper, and same relation he has been used over there. Whereas author Kaya also he has used, but the time constant they are K1 to K4. In the last, I will discuss that Kaya author's paper. This is the time delay controller, TD SMC. So sliding surface is a coefficient, some constant coefficient multiplied by your error function. So that is E1 is the SP like error, and this E1 of t, that is error SP like error is given by equation 30. So for perfect model, process model, and model, Em of t equal to 0. Therefore, outer loop is designed using TD-SMC. Means at outer loop, I am using TD-SMC. The control law is represented by equation 31, and where S of t is the given by Ks Sgn of Km E1 of t, and remaining Kd and Ks are given by the equation 33 and 34, where Kp and in this relation Ks equal to 15 Kp, Kp is the PID controller gain. Then these are the governing equations for the outer loop. As I told you earlier, the outer loop I have considered it as a SOPDT. Later on, this SOPDT it has been further reduced to the FOPDT and all that. So Please pay attention here. Outer loop is SOPDT and inner loop is a strictly first order only. Then design of SMC for the inner loop. For this, the sliding surface, it is represented by equation 37, and taking the derivative of what we get, e2 dot t plus lambda 2 e2 of t equal to 0. Then this substitute this error expression, because et equal to that reference value minus output value. So e1 and e2 you will have to put over there. So you will get a equation 39. The process transfer function, it is first order. Then its time domain representation is equation 41. Design of same slide. So from equation 41 and 23, 23 means that minus y of t plus lambda et equal to 0, and this 41 equation. We get the U equivalent control input for the inner loop as a equation 43. And obviously the switching control law is what? That tangential hyperbolic function. And therefore the inner loop SMC controller is given by equation 45. Now we are going to design a SMC for the outer loop. So outer loop is a SOPDT, and that is approximated as represented by equation 47, where this tau dA, this tau dA term, that is the delay term, it is used in the PD controller. I will tell you later on this. So here model is separated into two parts here, invertible and non-invertible. Then this is the SMC design for the outer loop with equivalent transfer function as equation 54, and same again the tangential hyperbolic function, and 56 gives you the outer loop controller expression, PD control. So this is this PD controller is used to remove the steady state error, and KP1. In this 57 equation, KP1 is the proportional end, tau D1 is derivative time constant, and these are the parameters given for the PD controller over there. So GP1 means outer loop process transfer function, GP2 inner loop process transfer function. '62. So these are the parameters. K1, sorry, K1, tau 11, tau 12, tau D1. For outer loop, these parameters for outer loop are listed here, and parameters for inner loop, they are listed over here. And for the approximated model, K, tau A, tau D, these are the parameters. These are the tuning parameters over here. And tuning parameters, different tuning parameters for single feedback. CC means cascade control, and ICC means improved cascade control structures. So I'm comparing single feedback, then cascade control, internal improved cascade control, then for inner and outer loop SMCs they are implemented. Means I am comparing the SMC structure with single feedback, cascade control, and improved cascade control. As for outer loop, same.
Hello, sir. Laware, sir. Participants, sorry for the inconvenience. Please wait in the session. Sir will join soon. Participants, sorry for the inconvenience. We are connecting with Laware, sir. There is some internet issue at sir's side. So please wait for few months. We will connect with sir and we will let you know this will be further proceeded or not.
रिपीट करू ना. एक मिनिट हा सर.
Sir, now your video is visible.
Yes,
You can share the screen.
Marin John madam.
Yes, sir.
Yes, okay.
Sir, you can share the screen now.
स्क्रीन नहीं दिख रही मैम.
No, sir.
अरे यार.
हाँ.
अभी
हाँ, yes, sir.
दिख रही मैम.
हाँ, yes, sir. Yes, sir. It is visible.
Ma'am, please tell me
Make it full screen, sir.
from where
Full screen,
it has
full
been
screen.
disconnected over there. Marin ma'am.
SPSMC. हाँ.
Design of SMC for
Outer loop out.
outer loop, inner loop हो गया.
हाँ.
ये हुआ ना.
Yes, yes.
Yes, okay.
Sir, please make it full screen.
Yes, 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 ma'am. Yes.
Yes, sir. Now it is perfectly.
Is it okay, ma'am?
Please. Yes, sir. Yes, sir. Please proceed.
From which slide, ma'am?
Not in this simulation results.
This one?
And this is done. Sir, it was a design page, something like that. This page, sir. This
slide?
This conclusion slide.
Okay, conclusion. So, from predictive structure based SMC, it has been elicited over there, which gives you the better performance than the prevalent control strategies over there. And as for the results obtained as simulation, the set point change and external disturbances under this condition, the predictive structure based SMC. Predictive structure means your time delay controller, your ESP controller, and IMC controller. This gives you the more robust performance. And obviously, as Nelder-Mead optimization algorithm gives you the tuning equation, which makes implementation easy. Now, in case of heat exchanger system, manually we are finding the parameters, or manually we are applying the parameters. As per my opinion, I don't know whether you are agree or not, but as per my opinion, by trial and error method or by heuristic approach also, you can call it as a one sort of optimization also, but that is the manual optimization. In case of predictive algorithm also, a Nelder and Mead, sir, that is not efficient one, but that Nelder-Mead optimization algorithm with the equation gives you some optimal results over there. So that is also one sort of optimization. And now from contribution 3 to 5, I am using non-traditional optimization algorithms. So here, basically, my aim is to tune the SMC parameters via the evolutionary optimization algorithm, and I'm using here weighted objective aggregation approach. Aggregation means single objective functions, they are finally added over there, and that is called as a aggregation approach. Then desideratum or aim of my contribution is to find or to propose an optimal design of SMC and exploitation of NSGA2 and that is non-dominated sorting genetic algorithm. Second, and multi-objective PSO, particle sum optimization algorithms. And based on this, whatever the best parameters I am getting, I will collect and I will implement, or I will have the real-time experimentation over there. So consider the single input, single output, a certain second order plant. So in this equation 63, y of t is the output AN, BN, and CN, these are the nominal or estimated plant parameters, whereas delta A, delta B, and delta C, these are the model uncertainties over there. And U of t is the control input, and final term dt, it shows it is nothing but the external disturbances, and obviously t is the independent time variable. Now, this equation 63, without uncertainty, it can be rearranged as a equation 64. And this dt, u of t, because your disturbances, they are entering through the input channel means through u of t. So here I have written dt u of t is the lump uncertainty, and that satisfies mod of d is less than equal to d max. D max is the maximum disturbances over there, and this dt u of t is plus minus the uncertain terms as represented by equation 65, and its upper bound is nothing but what? Plus delta A, delta B, and delta C terms over there, and tracking error it is there, where this R of t is the command signal or reference signal or set point signal, and Y of t is the measured output signal. FOSMC, that is the first order SMC. This sliding surface, it is as per the Yudkin sliding surface, it is there, and for n equal to 2, I am getting the sliding surface as alpha lambda et plus E dot t. So this lambda is greater than 0, means it is a positive constant, and this lambda I will have to find using NSGA2 and MOPSO algorithms. So taking the derivative and substituting E double dot expression into it, I am getting the equation 74. And if you place this 74 into 70 equation, means E double dot term, if you substitute E double dot term into equation 70, you will get a S dot T term, and control input obviously is the addition of switching plus equivalent signal. Then this is the without lump uncertainty or that disturbance term. U equivalent means equivalent control input is represented by equation 74, while switching control input is k SGN of S of t, where k is greater than d max and k is positive constant. Later on, this boundary layer thickness is the parameter in the hyperbolic tangential function. Putting this 74 and 75 into 72, 72 is this one, S dot t term. So I am getting what? S dot t equal to minus k SGN S of t minus dt u of t. This is very important equation as far as stability it has been concerned, by considering the Lyapunov function. So this S dot t equal to minus k SGN S of t minus dt u of t, equation 76, will have to put into the Lyapunov equation. So stability analysis of FOSMC, that is first order SMC. For this Lyapunov direct candidate function, it has been chosen as a v of t equal to 1 by 2 s square t. And if you take the first time derivative of that, then we get S of t into S dot t. And here you will have to put the equation 76 into this as a S dot t term. So I am getting what? S of t in bracket this S dot t term. So that is nothing but the minus k mod of S of t minus S of t dt u of t. So instead of SGN of S of t, I can write mod of S of t divided by mod of S of t divided by S of t, mod of S of t divided by S of t. S of t will get cancelled, and I am getting this S of t, and multiplied by that dt u of t term. So that is equal to less than equal to minus of mod of S of t and k minus dt u of t. But dt, maximum value of dt u of t is d max. So k minus that d max is the sliding condition, means this implies k must be greater than, that is the switching gain must be greater than the maximum disturbances d max. This one, k it should be greater than the d max, and this is called as the stability condition. And with this, k is greater than d max, your v dot t becomes the negative definite Lyapunov function, and once it becomes the negative definite function, means it is the asymptotically stable system. Here I can select switching control as a k into s of t divided by mod of s of t plus beta, means sigmoid function I am using. Three types of function you can use in the sliding mode control. First one is a classical switching control as a k sgn of s of t. Second one is a sigmoid function like k s of t divided by mod of s of t plus beta, and third one it is a tangential hyperbolic function as a k and tan h s of t divided by beta or omega. Okay, so and if you use the sigmoid or tangential hyperbolic function, that is only for the only for reducing the chattering, and resulting control input is u of t given by equation 82. Okay, so that first term up to k, it is nothing but the equivalent control, and final term it is the switching term. NSGA2 algorithm. So very first, this non-dominated sorting genetic algorithm too. It has been invented by the Deb Pratap K, professor of mechanical department in the year 2000, and now he is at Michigan University, and he invented first NSGA. NSGA in the 1994 with the complexity of OMN cube. OMN cube. So n is the population size, m is the number of objective functions over there. So obviously the complexity of NSGA, it is more than the NSGA2, because this for NSGA2 your complexity is OMN square, and for NSGA it is OMN cube. So n again multiplied by 1n. So that complexity increases for NSGA2. Then it uses an elitist principle. Elitist principle means elite solution. Elite solution means the best solution over there. So these are the characteristics of NSGA2 method. It has been mentioned in the paper proposed by Dev Pratap Kesar. So crowding distance means it's a distance between Pareto front solutions over there. Whatever solutions you are getting, the how solutions they are arranged, or at what distance they are arranged, is nothing but the crowding distance. And these are the advantages: explicit diversity preservation mechanism, overall complexity of, already we have discussed this. Elitism does not allow allow an already found Pareto optimal solution to be deleted, and disadvantages is this one, 2n size. Dear participant, this NSGA2 method, very simple concept it is there. Generation and number of populations you will have to define over there. Generation, say suppose 10 generations you are providing over there, and population size is 30 suppose. So in the first generation 30 iterations will be there. In the second generation 30 iterations will be there. In the likewise in the 10th generation 30 iterations will be there. At what happens at each iteration, key solution first gets compared with the second. Solution first will get compared with the second, and whatever the best solution as per the lower bound and upper bound of decision variable. Decision variable means what? The controller parameter, like sliding mode control, sliding surface, lambda. Lambda is the parameter of sliding surface, then k is the parameter of switching gain and all that. So all these are called as decision variables, and for this decision variable you will have to have the bounds, lower bound and upper bound, and based on this lower bound and upper bound the best solution it is found over there, and the solution which is not best, it is discarded. Again that best solution, it is compared with the subsequent solution. So solution, they have been arranged as an optimal solution, and that optimality or the figure or nature is called as a Pareto front over there. Already we have discussed this Pareto front in the M3 and all that subject. So these are the general step of NSGA2. Random initial population generation, it should be there, and in the MATLAB command you will have to use the RAND command over there, and evaluation of generated solution as per the objective function. Means, dear participant, objective functions will have to prepare objective functions and decision variables, means controller parameters will have to define, and for objective function it may be the minimization of objective function is there, or maximization of objective function is there. If minimization it is there, at the time of mentioning you will have to use the max. Say suppose first objective function is j1, then you will have to use max j1. Then you may get wonder, if we are minimizing the objective function, and then why we are using the max? Because the transaction is from minimization, no doubt, but that is from maximum to lower side minimization. Okay. Then the selection of the best solution having the higher fitness value, and means whatever I'm telling you, this is nothing but the NSGA2 general step. First solution gets compared with the second, whatever the best solution it is there, again that is compared with the third one, fourth one, like that, and finally the best solution it has been picked up. That's all. This is the MOPSO theory. So here V stands for velocity, and that VIG, I is the particle, IG is the dimension, and K is the counter over there. V is the velocity, and equation 84 gives you the position. The position and velocity modifications of the particle are represented by equation 83 and 84. So here initially instead of x is a constriction factor that is given by equation 85. Actually here what is happening, P based and G based. Public based, P based means public based, G based means global based. Flock of birds it is there, and in search of food they are flying over there. Okay. So initially they are scattered. Initially the birds are scattered, and finally they are in a single row. So that's the concept. So that P based, personal based is what? Bird, they are flying their own. That is the P based. And when they are coming in line with the others, then that is the G based. And that position or velocity is the that velocity is the best and personal best. Personal means individual birds it has been concerned, and G based means global based means all the birds, concerning to all the birds, they are it is concerned over there. Simply here the basic concept is comparison. It is there. First current position, next position, whatever the best position in search of food it is there, that will get preserved over there. That's the meaning. And X is the constriction factor, C1 C2 are the cognitive and social acceleration constant, and R1 and R2, these are the random number between 1 and 0. So here this psi it must be set as 4.1. Already it has been mentioned in the Deb's paper, and constriction factor is 0.729. Okay. So these are the standard guidelines over there, and accordingly you will have to select this one. Then proposed algorithm for tuning the SMC. So very first, random value of lambda 1 k1 beta 1. Lambda 1 k1 beta 1 it is for NSGA2 algorithm. Lambda 2 k2 beta 2 it is for MOPSO algorithm. Then I have been with the objective functions IE, IAC and their aggregation. Aggregation means IE plus IAC, and weight it has been assigned over there. W1 and W2, these are the weight. These are the generalized weights over there. So you will have to evaluate there as per the number of iterations over there. So this is the details of control algorithm NSGA2. So here define SMC parameters, lambda 1, beta 1 and that K1. Okay, then define the objective functions and constraints. So this file y cons, y is the objective function, and global variables lambda 1, k1 and beta 1, these are the controller parameters, or that is called as a decision variable. Then default structure, it has been created over this, and NS02 parameter you will have to provide over there and run the optimization. So here x1, x1, x2, x3, these are the three state variables, and you'll have to assign to the controller parameters over there, and you'll have to evaluate SMC parameters like lambda, k and beta, and objective function values like p1, p2 and p3 over there. That's all. Then I'm making the cost function as a 1 by 1 plus pi, that is each cost function. So why I'm taking 1 by 1? To remove the divide by 0 error over there. Then it's very simple. Initial random population you will have to generate, evaluate IEIS objective function evaluation, it is there, and then evaluate that controller parameters over there. Same like MOPSO, same it is there. Only in the PSO loop, iteration counter it is there as a G and K over there, and find out the best value, global best value and personal best value over there, and find the controller parameter as well as objective function values. Then first simulation we will study this transfer function FOPDT model. It is for the level control system. So here 0.86 is the static gain, 35 is the time constant, and 4 seconds is the delay time over there. Approximate pad approximation I have been used over there, and I'm getting equation 88. Okay, and conventional sliding mode parameter, by trial and error method I am selecting lambda equal to 0.5, k equal to 5 and beta equal to 0.1. So here these are the algorithm specific parameters of NSGA2: number of generation, population size, tournament selection, crossover mutation and crossover fraction and mutation fraction, stopping criteria and all that. Okay, so my optimization will be start at number of generation 100 over there. Then this is one NSGA2 base. What is I have conducted the total 6 trials over there, and I'm getting lambda 1, k1, beta 1, p1, p2, p3. P1, P2, P3, these are the three objective functions, and these are the 3 parameters lambda 1, k1 of NSGA2. And now what I will check, minimum value of objective function. So here trial number 6 gives you the minimum P1, P2 and P3. That's what the corresponding value to that minimum objective function lambda 1, k1 I'm picking as a 0.175 and all that. So trial 6 I will select over there. Then MOPSO, these are the algorithm specific parameters over there that we have been discussed. And here if you observe trial number 4 gives you the minimum value of the P1, P2, P3 objective functions, and the values corresponding to the that are nothing but the controller parameters. So these are the simulation, that is the convergence of the fitness function. So here if you observe here, first graph is a multi-objective fitness function, means P3, that is the aggregation approach. Then second one is a IE, and third one is a ISC. So how it converges to the 0, what will be the convergence point of that, that is I will tell you later on as a tabulated form. Then this is the simulated response output. So for PI Mercader and PI IPDT, the beauty of this paper is that Huba is the author. Huba author told me you have been used FOPDT model. You have been used FOPDT model without taking or without doing the modeling of a system, convert that FOPDT model into IPDT model, and then show me the response. So PI and PID, about 2 controllers, they are I have added after the revision over there. So here SMC, NSGA2 SMC and MOPSO SMC, this is actually 0 to 40% tank level is there, and that tank height, it is 26.5 centimeter over there, and this is the controller output. If you observe NSGA to SMC, you are getting red color peak. Red color peak, it is much higher than the others, but the convergence is earlier. If your peak is more, then convergence is earlier. This is the simple concept over there. Then this is the similar time domain responses, settling time, rise time, overshoot, and that objective function values for all the strategies over there. And this table number 14, it has been taken from this figure 33. Then the error signal plot and the sliding surface variations are there. If you observe the sliding surface here, NSGA2 based sliding surface, it reaches to 0 earlier than the other methods. Then this is the robustness analysis, that is the set point change, it is there, and corresponding controller output, it has been shown over there. Then this is the robustness analysis as a disturbance response, that is 20% parametric uncertainty and external disturbances. Now this is the IPDT model. From FOBTT model itself, I have been derived IPDT model, and then I have designed the PID controller for the IPDT model, and PID controller is obtained by NSGA2 strategy with this lower and upper bound, but I have been never included over it. So this is the NSGA to SMC Pareto front. These are the solutions. So NOP means number of Pareto front solution 55, and for MOPSO I am getting 18 over there. These are the solutions. So why NSGA2 strategy is better than MOPSO? Because ineffective solution it is in MOPSO, and if you observe the Pareto front solution of MOPSO, they are scattered over there. Whereas for the NSGA2, it has not been scattered over there. Okay, and the convergence of objective function for NSGA2 is obviously it is earlier than the other strategies, right? Then empirical results indicate that MOPSO is weaker than the NSGA2 as far as spread it has been concerned. So these are the metrics group: convergence, diversity matrix, and statistical result. NOP, MID, later on I will tell you, spacing, hypervolume, mean mode, standard deviation. So metric group MID, mean distance, average distance, number of Pareto front solutions already we have seen. MID is given by equation 92, and that NOP and NOP it is included under this MID, and CI is the parameter. This M is the, in case of CI, M it is number of the objective functions, and PI is the objective function value after last generation, means 100 generation. So here spacing is the actually basically the standard deviation here. So here NOP, MID, spacing, hypervolume, these are tabulated over there, and mean mode, median, standard deviation, it is there. So based on this comparative matrix, which algorithm, either NSGA2 or MOPSO is better, that is concluded. Then comparative matrices like decision variables, lambda, k, and beta. These are the decision variables or controller parameters, and related to that, mean mode, standard deviation, it is there. Again, it is mean mode, standard deviation. They have been calculated based on the objective functions. Same treatment is for MOPSO based SMC. So these are the Pareto front solution, NSGA2 and MOPSO algorithms. So better scattering for the MOPSO, it has been observed. This is the real-time experimental setup. It is there available in my laboratory, control system engineering laboratory. So here this is tank 1 and tank 2 with the handheld V1, V2, V3. Okay. Level transmitter whose output is 4 to 20 milliampere DC. It has been applied to the BNC connector 2120 analog input at both the tanks. I am using only one tank here. and then controller output is 0 to 5 volt, and that controller output is given to the BNC to 1205 analog output 1, and from this it is given to the V2I converter and finally to the VFD, and this VFD it controls the pump. Pump is nothing but the positive displacement motor it is there. So these are the experimental specifications over there. Height of tank, as I told you earlier, it is 26.5. These are the classical SMC parameter, lambda, K and beta, whereas for NSGA2 it is lambda 1, K1 and beta 1, and for MOPSO it is lambda 2, K2 and beta 2. It's open loop. This is the closed loop experimental response over there. 0 to 2, but that multiplier is a 20. 20 means 40%. 40% will be there, and I am comparing SMC, classical SMC, NSGA2 and MOPSO SMC corresponding the controller output U of T signal or control efforts is shown here. NSGA2 base SMC gives the better performance. These are the time domain specifications. Again, this is the error signal sliding surface. It is there. Earlierly, it converges to 0 for NSGA2 SMC. Then this is what your disturbance response, 20% uncertainty and external disturbance response. To the tank, I have been connected relay, and for particular 15 seconds, I'm operating that relay and giving the disturbance. Or you can add the water from upper side of your tank, then that will also the disturbance. So this is the set point change and corresponding controller output U of T. So here NSGA2 SMC gives you the better performance as compared to the other strategies. Then very similar it is there, but only how the objective function it has been modified over there. That is the contribution fourth. So same NSGA2 I have been used over there, but how how objective function you can modify. So here tracking error already we have seen. This is my F1 and F2 objective function, and I'm aggregating that as a F3. But here W1, W2, W3, W4 weights I am adding over there. Okay, and that is called as a equivalent weight. And whereas this for F3 I am applying again important weight over there. Later on I will tell you these equivalent weights, how W1, W2, W3, W4 weights they can be assigned. Okay, so here concept of dominance it is there already. We have seen the Pareto front. In the Pareto front, concept of dominance is given by X dominance Y. If F1X is less than equal to F1Y and expression. As I told, author Kaya also contributed much in the process control area and in the domain of sliding mode control. So here K1, K2, K3 and K4, these are the coefficients of sliding mode control, and U equivalent is given by this one. Kaya paper, stable sliding mode control for stable processes, and here I think it is 2008. So here he used the switching function as a tangential hyperbolic function over there. So this is the multi-objective criteria. Why multi-objective? Because here F1, F2 and F3 these are used over there. That's what it is a multi-objective criteria. So general objective function is given by this Wi into Fo. Fo is the objective function. Wi is called as a equivalent control weight. And this is the based on the percent contribution. These weights you can fix over there, right? And in equation 102, this epsilon I is the mean value of the solution of objective function, and epsilon n is the mean value of objective function. Importance weight. Now these are equivalent weight. Now importance weight is what? W is the importance weights. So how this can be happen over there? So in the first objective function f1, in the first objective function f1, w1 IE plus w2 ISC. So here percent contribution of IE and ISC is this one. That's what where weights are 0.6. First 57 means related to the 0.6 and 42.4. So that is the 0.6, 0.4 and W3 0.9, 0.4. So based on the percent contribution or standard deviation, that weights it has been applied over there. Okay, but the addition of weight, it should be 1. Addition of weight should be 1. So weight assignment for F1 and F2 is the 0.25 and 75, and W5 W6 it is given here. And here modified cost functions or objective functions, they are f1, f2 and f3. So based on the percent contribution and standard deviation, you can modify the objective functions. So these are the NSGA2 parameter. I have changed from the previous experiment, that is the number of generation 60 and all that, kp, kd, ki. Now in this I am changing the here crossover fraction and mutation fraction. Crossover fraction means PM and mutation fraction means PC. Crossover fraction is PC and mutation fraction is PM. So I'm changing the PC and PM and finding the value of controller parameter lambda, k and beta. Okay. So for NSGA2 parameter, again for objective function, I'm changing with the PC and PM. So result table. So from that, I'm deriving the decision variables or controller parameter. For NSGA to Kaya SMC, same procedure I am utilizing over there and finding the controller parameter as well as objective parameter. This is the, again I have done the modeling, and now at this time I'm getting this approximate model and FOPDT model like this. So these are the experimental time domain and objective function representation over there. Set point change, corresponding control efforts, sliding surface variation, error signal variation. Then U equivalent, what should be, how U equivalent will get vary, that will be shown here. And U switching signal also I have shown experimentally. And this is the robustness set point change. Disturbance test. So conclusion, that is the how you can modify the functions, that is based on the standard deviation and percent contributions of the term in the objective function. So no doubt here, if you use the bio-inspired optimization algorithm, your performance will get enhanced. But again, much depends on your objective function and how you are assigning the weights to that objective function, and then or the weights to that terms forming the objective function. Based on that also, performance of any process, power system or process control system or motion control system depends. And from this paper I am getting the relation, that is sigmoid and tangential hyperbolic relation, delta equal to 1.5 to 1.7 beta. This expression I am getting over there. And last one is a global optimization. So here I'm using the Jaya optimization algorithm and ABC optimization algorithm for second order sliding mode control. So for Jaya and ABC SOSMC, I'm comparing with the classical SOSMC. Typical SMC means first order SMC, then NSGA2 first order SMC and PID. So same we have discussed this. Now here what is changed, only the sliding surface, it has been changed. I am taking the sliding surface as a 114 represented by equation 114, and now take the derivative of that 114 equation. I am getting S double dot plus beta 2 S dot T and eta 2 E dot T plus E double dot T. Now you will have to put the expression for E double dot T in equation 115, and you will have the 116 equation, and put then 0 as a stability condition over there. So I am getting the equivalent control signal as a represented by equation 118. Then this is the switching expression represented by equation 119, and all are positive, and this gain, it must be greater than maximum disturbance divided by C value, where C is the nominal parameter over there, right? And Lyapunov function I am taking as a half S square T plus half S dot square T, okay, and put the value of S dot T square in equation 1 to 1 to find out the stability. So this is the stability. I'm getting stability as a KSW2 is greater than D max by C, which monopolize or which dominates the uncertainty in the system over there. And I am getting lambda 2, it must be greater than 1 by C, and mod of S of T equal to mod of S dot T, it should be greater than 0. These are the sliding conditions. And finally V dot T is the negative definite, and nothing but the it shows the global asymptotic stability. Okay, then this is U switching as a tangential hyperbolic function and total control input for SOSMC. I am taking the reference of this 1 to 5 and implemented all the strategies based on this U of T. Now Jaya algorithm. This Jaya algorithm is represented by equation 1 to 6, and where X is the updated solution. X DCI new is the updated solution, and D is the decision variable, C is the candidate, and I is the iteration over there. So what is here? Basically, this Jaya algorithm is called as a best and worst algorithm also. Means only in the optimization process, you will have to select the best values and worst value. Best value minus current value, and worst value minus current value, and you assign the weights as a R1 DCI, R2 DCI to it, and that's the Jaya algorithm. Basically, Ravi Pudi Venkatrao, professor from mechanical department of NIT Surat, he invented this Jaya algorithm. Actually, Jaya is the name of his daughter. So here I'm taking J1, J2, J3 and J4 with the weight assignment based on the previous contribution. I'm using this 5. Next one, yes, 5 objective functions over there, and same strategy like NSGA2, and I am using over there, and optimize the SOSMC parameter and objective function values. Then this ABC algorithm, in ABC algorithm, total 3 bees are there. Actually, these are the honeybees, and they are looking for the or they are in search of food or best food. So these bees are the onlooker bees, employed bees, and scout bees. Actually, the employed bees, it found the source of food. Okay, then that employed bees passes that information to the onlooker bees, and then scout bees, whatever the bad honey it is there, that gets discarded by the scout. So this is the natural example, and based on that, this ABC algorithm works. So here in technical language, that probability functions are defined. Actually, there are 3 types of stages. Initialization means it is related to the employed bees. Then search phase means it is related to the onlooker bees, and scout means discarding the bad honey or discarding the bad solution is done by the scout. Okay, and some best solution, they are preferred by the onlooker bees. Okay, so this is the connection, natural connection with the technical, what we can say, this technical issue here. So here 132 and 134, it is nothing but the probability function and the cost functions are there, whereas this V, velocity, and X best and position, these are given by the onlooker, employed, and scout bees. So X best position is onlooker bees, and expression 137 is it is related to the scout bees over there. Okay, so same. Define the objective function, specify the decision variable, lower bound, upper bound, then define the algorithm specific parameter, then define the counter, find out x best position, and then finally evaluate decision variables and objective function. These are the ABC algorithm details. So simulation already here in this third order transfer function with time delay I have been considered. Again, I am reducing that third order transfer function with delay to the FOPDT, because might that that is easy for the designing the SMC. Either by Taylor series or Paddy approximation, you can have 140 numbers equation for the implementation purpose. Then for Jaya algorithm, my LB, that is lower bound and upper bound is this one. So 5. Lower bound is all 0 and upper bound is this one. So controller parameters are 5. That's what 5 entries must be with the lower bound and upper bound. These are the Jaya algorithm specific parameter values. Then this is eta 2, beta 2, lambda 2, KSW, and omega 2. These are the parameters of Jaya algorithm. Okay, and I have been consider here 5 experimental trials over there, and at third trial. Now compare these 31 and 32. 31 and 32. Third trial gives, just look at table number 32. At trial number 32, I am getting minimum value of objective function. That's what I have picked up the setting like 3. Now concentrate on table number 31. So I am getting eta 2, beta 2, lambda 2, KSW, and omega 2 as per the trial number 3. So best value will be that one, and worst value will be this one. So I am finding always each time best and worst values. So this is the simulation test. First, it is the cost function value, that is the convergence. So if you observe here, somewhat steady and regular pattern it has been observed for J1 to J5 objective function, and this paper it consists of experimental trends of controller parameter as indicated by in the B figure. Okay, and this one objective function C is the objective function after 60th iteration, and this is the intermediate objective function pattern, that is the after 5th iteration. So after 6th iteration you are getting uniform pattern increasing and decreasing over there, whereas here some complex objective function pattern you are observing over there. So this is for Jaya SOSMC pattern. Next, ABC based SOSMC, only give me 5 minutes. These are the algorithm specific parameters and all that, and these are the parameters selected over there. So same trial, like a Jaya optimization. Trial number 5 gives me a minimum value of objective function. So I'm picking the trial number 5 parameters as a final parameter over there. So this is the ABC algorithms trends. Actually, you may call it as a learning curves of ABC algorithms, and these are the algorithm specific parameters. Optimization result for NAGA2 base. So here it finishes the ABC algorithm. Now for comparison purpose, NSGA2 first order SMC I am also implementing over here. Same treatment I am getting over there, and I am getting very irregular pattern as far as D and C figure it is concerned over there, and also from B figure very much variation I am getting over there in case of controller parameters over there. So this is the convergence point of 3 algorithms, Jaya, ABC, and NSGA2. So if you observe here, very earlierly Jaya SOSMC parameters converges. This is the simulation test. This is the step response for the nominal conditions for Jaya ABC, conventional, NSGA2, Camacho SMC, Jaya SMC, SOSMC, and all that. Okay, so this is the performance analysis in case of time domain and all that. So that green colored quantitative green color shows the quantitative analysis, and which shows Jaya Jaya gives you the better performance. Then I have carried out the statistical analysis in between Jaya ABC and NSGA2, best, mean, worst, standard deviation, average evaluation time also. So for Jaya algorithm, if you observe, you will get a less average evaluation time over there. Then up to J5 means for 5 objective function I am carried out the statistical test. Also Friedman test, Dunes test, p-value test, CET test I am finding as a statistical test to confirm which algorithm is the best one. So Friedman test is given by this 141 equation, while AC is the standard error. Standard error in three algorithms is given by equation 143 equation. So CET is the critical time efficiency, how much time that particular algorithm takes to provide the objective function values and controller parameters value. Also rank assignment I have done here. So for best solution, rank first it is there. For worst solution, less rank it is there, and for meanwhile the medium rank it is there. So rank assignment it has been done over there, and that is given by the Friedman test. So all these Friedman test, Dunes test, all these tests, they are the data test. Then Dune test. For this Dune test, actually pairing of algorithm it is concerned. So if you observe Jaya ABC, Jaya NSGA2, ABC NSGA2, the p value standard error it is there, R mean value it is there. So this is the statistical Dune test, and its CT it is there. City, not city, city. That is the it is the time resources utilization parameter or attribute it is there. So here ABC shows 1, means as per city test ABC is the better than the Jaya and NSGA2 FOSMC. In all remaining cases Jaya is the best. P-value test. So these are the three tests for Jaya, same three tests for ABC and NSGA2, and I am getting the p-value. Less p-value must be there. If less p-value it is there, better is the optimizer. Then this is the elevated date time process for FOSMC, first order SMC. U of t it is represented by 147 equation, and these are the optimized value and objective function values for elevated date time process. For SOSMC strategy, the final total control input is given by equation 148 and its values. Then I have taken the moderately oscillatory process over there for FOSMC and SOSMC strategies over there with U of t and their switching control input. So this is for the examples. Moderately oscillatory process and all I'm getting. Still here I'm verifying which algorithm is the best. So still I'm getting the Jaya is the best. So for this real-time test, open loop test, it is there, which shows model level and actual levels. They are coincides each other, means best fit it is there. Then this is the nominal process response over there, and here I'm getting that black A Jaya. Jaya is the best than the other one. So in the first lecture, might Dr. Raja told that variations in the PID controller is less than the sliding mode controller. My dear participant, I am not agree with this, because if you observe, your pink color is variation in the PID controller, and whereas that green color and blue color, these are the variations in the J and ABC. Means based on these are the SMC variants actually. So SMC variants gives the less variations in the control efforts. So these are the time domain specifications, and from this time domain specification represented by the green color, they are superimposed over the other. Yeah, objective function. So this is the typical performance in terms of tracking error and sliding surface variations for all the strategies. This is the 10% uncertainty and the disturbances are real-time performances for 10% uncertainty and external bounded matched disturbances. So conclusion verifies the invariance property and set point tracking and disturbance rejection capability. It is very good for the bio-inspired algorithms, and it shows the fast convergence of sliding surface and tracking error as well as controller parameter. And Jaya shows the better performance than the other reported strategies. What I found here, online controller tuning is not possible because each time I am conducting the simulation test and taking the parameters based on the minimum of objective functions, and then I am applying that parameter in the real-time fashion or in the real-time manner. Why this is so? This is so because the actuator of that hardware can't cope with the parameters which are updated for every second. Okay, so this is what the actuator limitations it is there, and for the future work the large scale data sets needs to be experimented over there. So this is the conclusion. Open research area, I have actually attended graduate school on SMC at IIT Jodhpur, and here Antelona Ferreira madam, he discussed open research area as a integral sliding mode control. Dr. Bandopadhyay sir, he told ki now ample of opportunities in the higher order sliding mode control. It is there. Event trigger sliding mode, Abhishek Kumar Behra, he told ki event trigger sliding mode, ample opportunity. SMC variants in power electronics, it has been discussed by the Professor Deepak Fulwani sir, and optimization of SMC using non-traditional optimization algorithm by Sarah Swarjan madam, who is the inventor of sliding mode control. Sarah madam and Sarah madam and Friedman sir. He told that you can use the traditional optimization, but challenge is without using simulation, how online you can tune the particular process or particular hardware. And then SMC is the quantum computing. This is the very latest, but only one candidate from IIT Dhanbad, Singh Cheng, she works in the SMC, in the quantum computing using SMC. Okay, so these are my publications. That is global optimized second order, already we have discussed. Evolutionary discussed. Dynamic sliding mode control at the end of this month, this paper will get published over there. Then this one, normal terminal sliding mode, integral augmented optimization of robust Smith predictor control strategy, non-singular terminal sliding, then global sliding, Tito system, decentralized dynamic sliding, LMI based finite time sliding mode controller, then experimental constrained optimization of sliding mode controller with the modified objective function. We have discussed this, and temperature control of it. This one also discussed. And these are the only 4 conference publication. So selected publications I have mentioned here. References, these are the 40 references. And thank you. Is there any questions, please? Hello?
Participants, you can unmute yourself and you can ask your questions.
Hello, sir.
Sir, we have a question in the chat box. Which optimization techniques are best suited for SMC parameter tuning?
Which optimization technique? is the best suited. Basically, that optimization techniques, it depends on, no doubt, first algorithm specific parameter. But what I observe that recent techniques, that NSGA3 it is there. Actually, I have also implemented NSGA3, then ADG NSGA3. That is advanced diversity. NSGA3 also I have discussed. Due to time limitation, I am not able to show that. Later on, I will convey to the Dr. Ravindra Munje sir. But NSGA2, NSGA3, then Jaya algorithm, those using elitist principle, they are the best for the SMC parameter.
Thank you, sir. Participants, if you have any questions, please raise.
Front question. Good afternoon, sir.
Yes, sir.
Yes, sir, you're audible. Please proceed.
Thank you, sir. It is wonderful to listen to your talk on the sliding mode control and its different optimization technique. Sir, I have one question that is means the automation technique then between the single objective function and multi-objective function. So, which one is the more suitable technique when I selecting that single or multi-objective function in any kind of optimization technique?
Yeah, sir. Yeah. Very good question.
Sir, particularly for the non-linear systems.
Yeah. Sir, for as far as non-linear system it has been concerned, single optimization is the best. Okay. Single optimization is the best solution. But for linear, you can go for MO also. Or MOEA. MOEA also you can go for the MIMO system.
Okay. And sir, you have talked about the nailed and meet optimization algorithm.
Yes.
Okay. So nailed and I think that nailed and meet optimization technique, it is a one type of local optimization.
Yeah. Already, yeah.
So nailed and meet, apart from nailed and meet, and there's another one fmin-con technique also. It's available, I think. fmin-con, that is another.
Yeah. That is the available in the MATLAB also.
Yes. So this local automation techniques, is it really suitable when it can be? Is this chosen? Is it preferable for any nonlinear system optimization tuning parameters?
No, sir. No. Because what happens, sir, in the local optimization, maybe in between that population, if you specify the population and number of generations, if you use this local optimization, because variables you will have to define globally. So what all SMC parameters I have been defined as a globally. Okay, and locally if you define that parameters, then that optimization process may terminate intermittently. That's the basic disadvantage.
Thank you, sir. Thank you.
Yes, sir. Thank you, sir. Thank you.
Hello, sir.
Please, anyone else having
Good
any
afternoon,
question?
sir. I am Dr. Anand Kumar, sir. Hello, sir.
Sir, your voice is not audible. Dr. Anand Kumar, sir.
Yes, hello, sir.
Yes. Now you're audible.
Yes. My voice is coming, ma'am.
Sir, little louder, please.
Okay.
Dr. Anand, sir, please ask
sir.
loudly, sir.
Yes, sir. Okay, sir. I have one question, sir. When we select the objective function, in that you have chosen the weighted for the integral absolute error.
Pardon, sir, your voice is not clear, sir.
Okay, sir. Actually, sir, my question is that how can we select the weight ratio in the objective function for integral absolute error and the integral time absolute error?
Sir,
Hello?
can you type the question in the chat box? Because your voice is not.
Okay, sir. Okay, ma'am.
Sir, please wait for a minute. Let him.
Yeah, ma'am. Sure.
Sir, good afternoon, Munje sir here.
Yes, sir.
He is asking about how to select the weights in case of optimization function.
Already I discussed the weights in the contribution of 4. That is importance weight and general weight. 1 minute. 1 minute, sir. Dr. Anand sir,
Yes, sir. Voice is
are you
coming,
there, sir?
Yes, sir. I am there, sir. Okay.
Okay.
I am listening.
Sir, consider this F1, F2 and F3. Okay. W1,
Yes, sir.
W2, W3, W4, these are the weights. Okay.
Yes,
That
sir.
is called as the equivalent weight factors. Okay.
Okay.
So W1 plus W2, it must be 1. W3 plus W4, it must be 1. Okay.
Okay.
And outside of this, if you adding the weights to particular objective function, then that is called as a importance weight, sir. Okay.
Okay, sir.
Now this one, objective function. Fo is the objective function. You can take O as a 1, 1, 2, 3. Okay. Then taking the mean of solutions of objective function to the mean value of objective function, you can calculate CP also. Okay. Then based on the percentage contribution, here this slide, it is very important. In the first objective function F1, percent contribution of IAE and ISCE, okay, is this one. So 57.35% and 42 point means it is near to the 60%, and it is a for 40% I am taking. Okay, so weight will be what, sir? 0.6, 0.4. So 0.6 plus 0.4, 1. Okay, sir. So this is the first criteria. Another criteria is what? Standard deviation. Standard deviation of IAE and ISC, controller output U of t, and tracking error. So you can calculate, you can find the standard deviation of IAE and ISC, and the low standard deviation, you can give the higher weight. Okay, sir.
Okay, I understand, sir. Okay, I understand.
Yeah. Means based on the two factors, standard deviation and percent contribution, you can assign the weights and you can modify the objective function, sir. Yes.
More benefit of this using weight function in system response?
Yes, sir.
But in performance, what is the benefits of using the weighted objective function?
Yes.
Sir, what is the benefit of using these weighted objective functions in the performance?
Yeah, in the conclusion of this contribution, I told you. Still 8 minutes. Sir, not only modifying the objective function, you will get an advantage. Okay, sir. Very first thing. So you can modify the objective function, and you can have the trials on this PC and PM. Then you will get a better response over there. This one. So already this contribution is having better response than the previous one.
Okay, sir. Session was nice, sir. Okay, sir. Thank you, sir.
I hope there is no further question. Munje sir, can we conclude the session?
Yes, madam. We can conclude. Thank you, Laware sir.
Thank you, sir. And very first, I'm very much thankful to Dr. Ravindra Munje sir and Merin John ma'am, because you take a lot efforts for this workshop. And thank you very much.
Thank you so much, sir. We sincerely thank our speaker for an insightful session. Like being a speaker, in spite of being a speaker, he back from your side. Like we are seeing that you are attending other sessions too. So you have covered this parametric analysis, optimization of process planned models, and advanced sliding mode control strategies. Very clear and very practical explanations. Thank you so much, sir. Thank you once again to all the participants. Now we are concluding this session here, and this is to inform you that next session will be at 7 p.m. as we are having our next speaker, Professor Soran Gajik. He is joining from New Jersey. So due to this time constraint, we will be having our next session at 7 p.m. Kindly make a note of this. So thank you once again, sir, for this wonderful session. We are expecting your collaboration in future too.
Thank you. Thank you, Munjay sir.
Thank you, sir.